All right, guys, today we're talking about measurements and significant digits. The title of this unit, the book calls it Dealing with Uncertainty. And really what it comes down to is when you are reading a measurement, how accurate is that measurement that you're reading? So for example, if you were to weigh yourself at home, you stand on the scale, and let's say that your scale at home measures to the nearest pound. Okay. So it measures to the nearest pound. So you stand on the scale and it says that you weigh 132 pounds. If you were to write that you weighed 132.00 pounds, that would be misleading, because what you're implying when you write 132.00, you're implying that you actually measured out 2 more digits to the right than you actually had measured. Your measurement got rounded to 132. So saying 132.00 implies that it actually got rounded out to the hundredths place. So these two, even though they're the same number, even though they mean the same thing, when you're dealing with measurements, they are read very differently, or the assumptions that go along with it are assumed very differently. So what we call significant digits are the digits that you actually measure. Okay, the numbers that you actually measure are something that we call significant digits. So in this example, you actually measured 132, and the rest that you don't see, you just rounded away. So this 132 has 3 significant digits because you measured 3 values. If you were to write this number here, 132.00, what you're implying is that you actually measured 132.00 and then you rounded. So this number has 5 significant digits. Okay, and there's all these rules that you can read through. You might want to pause the video. I'm not going to go through all of them in detail, but pause the video, read through them really quick. And it kind of explains to you what is considered a significant digit and what is not. So for example, non-zero digits are always significant. So if there's numbers if you're reading the numbers and there's no zeros, those are always significant digits. Zeros that follow a non-zero and are to the right of a decimal point. So if someone were to write, and again, this is you as the reader. If someone were to say to you 4.20, that 0 is significant because that means that they actually measured out that far. All the stuff that comes after, they rounded away, but 4.20 is at least how far that they measured, okay? And the other example, 3.00, if they wrote 3.00, that's not the same as saying 3. That means they actually measured out to the hundredths place, not just to the ones place. All right. Zeros between non-zero digits are always significant, of course. If I were to say 4,002, that's 4 significant digits because the zeros come in between 2 other non-zero digits. Zeros to the left of the first non-zero. Now here's where you need to be careful. When you're reading decimals like 0.006, these 2 zeros before you actually hit a number are not considered significant. We would say that there's only 1 significant digit in this situation, and they're rounding to that value right there. All right. And then zeros to the right of the last non-zero are not significant. So for example, if I were to say 40,000, again, there's only 1 significant digit. These zeros are just placeholders telling me where my decimal is, but there's only 1 significant digit in this problem. All right. So here's a few examples. It asks us, this first one just wants us to practice this a little bit. It says to state the number of significant digits and imply what that means. So for A right here, it says a time of 11.90. Now, because they went 0.90, those are significant, and obviously the 11 is significant. So there are 4 digits that are significant in part A. And then it asks, what does that imply? Well, what that implies is that this is where they rounded. So that implies that this is an accurate measurement within 0.01 seconds. It's implying that they measured up to 0.01. All right, so part B. And to me, that's the easiest way to look at significant digits is how far did they go before they started rounding, okay? So a length of 0.000067 meters. So if you were reading this, all these zeros don't matter because they come before we actually hit real numbers. And at that point, we only have a 6 and a 7. So there's 2 significant digits, the 6 and the 7. And this is saying, if you were to read this, it's implying that they rounded 1, 2, 3, 4, 5 to the nearest 6th place. So 0.00001 meters. And that's a really accurate measurement right there. Well, I guess it depends on how big of an object you're measuring. Part C, a weight of 0.0030 grams. Because they wrote this 0, that's significant, and obviously the 3 is as well. So we would say that there's 2 significant digits. And then what that implies is that they rounded 1, 2, 3, 4 places. So 0.0001 grams is how accurate that measurement is. Part D, a population reported as 240,000. Well, we ignore all the zeros between the decimal, and we're only going to count the 2 and the 4 because it doesn't tell us otherwise. So this one has 2 significant digits, and it's rounding to that last number right there, to the 10,000th place. So this one is accurate to the 10,000th person, to the 10,000 people, the population. And part E, a population reported as 2.40 times 10 to the 5th. I like this one because they simplified it for you. They got rid of all those extra zeros and they just wrote exactly what it is. There are 3 significant digits, and part 2 wants to know what that implies. Well, that implies if I actually multiply this out, that's 240 and then 3 more zeros. So that's actually the same as above. So that's saying that they're reporting within 10,000 people. Okay. Let's look at a couple other examples here. Example 2, for each of the following operations, give your answer with the specified number of significant digits. So with this problem here, we need to be a little bit careful. Sorry to get interrupted there. It wants us to perform the operation and then round as it states. So for example A, 7.7 millimeters times 9.92 millimeters, and it wants us to give the answer with 2 significant digits. So when I multiply that, I'm going to go 7.7, and we're going to times that by 9.92. And I'm going to get 76.384. So 76.384. But it wants me to round to 2 significant digits. Well, 2 significant digits is just 7 and 6. So I'm going to round the rest of this away. And since this is a 3, this just rounds to 76 millimeters would be my answer there. Okay. The second example, 240,000 times 72,106, and it wants 4 significant digits. So if we take 240, 240,000, and we're going to times that by 72,106, And it gives it to us in scientific notation, which isn't a problem. 1.7305, 1.7305 times 10 to the 10th power, right? Times 10 to the 10th. So 4 significant digits would be 1, 2, 3, this value right here. So that would be 1.73. And because I'm rounding to this 4th significant digit, that would be a 1. And I would just drop the 5. And then I'm still going to put the times 10 to the 10th power. All right. If you have not rounded for a while, well, I feel like every year this is almost one of those things that we need to review, even though you've been doing it since my wife teaches like 3rd graders how to do this. So you've been doing it for a long time, but sometimes, I mean, it's been a while. Maybe you forgot some things. Go ahead, pause the video, read through this review really quick. If there's notes that you need to take to help you remember some of this stuff, go ahead and take those notes. Otherwise, I'm going to assume that you are comfortable with the basic concept of rounding. So pause the video, hit play when you're ready. Okay, let's move on. Maybe. Here we go. Pushing the wrong arrow button. So sometimes when we measure, we've got different types of errors. Obviously, all kinds of things can go wrong when you're trying to measure something, whether it's time or distance or weight or anything else. And I love this example of the baby because it's what life really is. So there's 2 types of error that we're going to consider, and the definitions are down below. You're welcome to pause the video and write those down. But the diagram here kind of represents those 2 types. So let's say you're at a doctor's office and they're trying to measure a baby. Well, I don't know if you spent much time around babies. They don't like to hold still very well, especially when you lay them on a giant metal plate. They're not going to hold still. They wiggle, they squirm. And so over here on the left, what you see is as they wiggle and squirm, their weight on the display bounces up and down a little bit. And if you look at that close, it looks like the weight is bouncing between maybe 4.5 and up to, it looks like maybe 15.0. It's looking like it could be anywhere in between that range. But the baby's wiggling, so we can't really tell exactly what the range is. Well, that type of error is what we call a random error, because that's not something that we can control. That's not something that we set. That's just an event that is happening and it's unpredictable, and we can't actually measure how much that wiggling is going to change the weight. Okay. There's ways that you could work around that. You could write down the weight 10 different times and take an average of those 10 different measurements, because some overweights and underweight measurements are going to balance out, and that might give you a more accurate measurement. But either way, that's called a random error. It's something that's unpredictable. You can't control it. The second error is, let's say they take the baby off the scale. And this is really depressing when you get off the scale and realize that it wasn't set accurately. So without the baby on the scale, it says that nothing weighs 1.2 pounds. So that means when the baby was on the scale, it already thought it was 1.2 pounds, and then it took the baby's actual weight and added to it. So this type of error, because that's an error in the system, that's a problem that's going to affect every baby that you put on in the exact same way, that's called a systematic error. That's not random. That's not unpredictable. We know exactly how much our measurement is off. It's something that we can measure because it's always going to be 1.2 too high. All right. So working with, and again, if you need to pause the video and write down those measurements, you're more than welcome to. Or write down those measurements, write down those definitions, go ahead and do so. Okay, so working with random and systematic. So let's say that before taking off, a pilot is supposed to set the aircraft altimeter to the elevation of the airport. So before you leave the airport on the airplane, you set your height to match exactly what the airport says. It's meant to help the airplanes be more accurate with their measurements. If a pilot leaves San Diego that has an altitude of 17 feet, which is great because it's basically right by the ocean. It's only 17 feet higher. And so if a pilot leaves San Diego with her altimeter set to 517 feet. So the question is, what type of error is that? Well, if it's supposed to be 17 feet, but hers is set at 517, she's 500 feet too high. Or she thinks that she's 500 feet higher than she actually is, which is terrifying when you're reading heights off a map and you think as you're flying that you're at 1,000 feet. So that 500-foot cliff in front of you is not scary at all until you find out that you didn't measure your altitude right to begin with. So looking at her altitude, she's going to think that she's 500 feet higher than she actually is. Well, that's not unpredictable. She made that measurement. She physically did that. We know exactly the difference. So that right there would be a systematic error. And hopefully she remembers as she's flying over the mountains that she's not as high as she thinks she is, right? Lap times in the Indianapolis 500 auto race. So things that could come up when you're trying to measure the lap times, especially if you're doing this by hand. To me, there's all sorts of random errors that could happen. Maybe you clicked a button just a little bit too late because you didn't notice the car. Maybe you're just really slow. Maybe you're not as fast at clicking the button at the right time. Maybe you got distracted or you accidentally clicked the button too soon or your hands got sweaty so your finger slipped off the button. There's so many things that could randomly make that time inaccurate or have an error if you were doing it by hand. Okay. If you were doing it with, I don't know, a computer, the errors might be more systematic. Maybe from the time that the computer thinks the car is going by and the time that it registers that it did, a really minuscule amount of time might go by for the computer to do its measurement. Well, that's a systematic error. It's just the computer processing time. Or I guess even clicking it by hand, it takes a minute for when you, not a minute, but it takes an amount of time when you click the button for the timer to recognize what you did. And that's going to give you a little bit of error there. All right. Okay. Size of errors. This one is near and dear to my heart because I don't believe any package that tells you how much is actually inside of it, especially when it comes to sour Skittles, because I feel like I get ripped off all the time. So size of errors, we have an absolute error and a relative error, which sounds pretty familiar because we talked a little bit about absolute and relative difference earlier in these chapters. So let's, for example, if I have this bag of sour Skittles, this is one of those big share bags. It's got like 78.4 ounces in it, okay? So I'm going to write that down here. This has 78.4 ounces. And the little boxes that you get that have like 13 Skittles in them, it says that there is 3.2 ounces in that box. Now, if the company comes out and says, you know what, our machines were off. When we measured out our Skittles, we were off by 1 ounce. We were off by 1 ounce on all of our measurements. Well, when you look at the great big bag, if I've got 70, if they're supposed to be 78.4, but they were, let's say they were 1 ounce under. So let's say instead of 78.4, they were only at 77.4. That's not that's not a big deal. That's 1 ounce out of almost 80 ounces. That may not seem very significant, but when you look at the little box, if they were 1 ounce under on that measurement, that means that you're only getting 2.2 ounces. That's going to feel a lot more significant. So the measured amount that it was wrong is what we call the absolute. So the absolute is the measured amount of error. So in this case, our absolute error is 1 ounce for both of these packages. We're just 1 ounce off. The relative measure is the one where we say we take what we measured it to be. So we measured 77.4, but there was supposed to be 78.4 ounces. And after I measure that, just like relative difference before, after I measure that, I'm going to divide it by my 78.4, what it was supposed to be. And then I'm going to multiply by 100. Okay, so I'm going to take that 77.4, I'm going to minus the 78.4. And I guess we should be careful because our absolute measurement is actually -1 because we're 1 short, we're 1 under, so that's a -1. So when I do the math here, when I say 77.4 minus 78.4, that's -1. And then I've got to divide that by what it's supposed to be, the 78.4. And then I'm going to times by 100. So when I do that, that gives me the percent, is how we read it a lot of times. That says -1.27%. So I'm only 1% under what I should be. But if you do the same thing with this Skittles box, if I take 2.2 minus 3.2, divide it by my measure, what I'm supposed to be getting, and times it by 100, all of a sudden that becomes a lot more significant. I get that -1 that I divide by 3.2, and then when I times it by 100, my percentage of error is -31.2, what did that say? 31.25%. So even though the absolute error was the same, the relative error is huge because you're losing a third of this box because of that error that they made in measurement. So instead of 13 Skittles, you're only getting like 8. All right. So the actual formulas, you can pause the video and write these down. Remember the absolute error, we just took the measured value and we subtracted the true value. And that just tells us how much we were off. The relative error is when you divide by that true value and then times by 100. So you can write those down, pause the video if you need to. But putting that into a couple examples here, and we might only take, the video's starting to get a little bit long on us, so we might only do one of these, at least on the video. Well, let's do part B in class, and we'll talk about the weight situation. So let's say that your true weight is 125 pounds, but a scale says that you weigh 130 pounds. Well, that's rude. It's not supposed to go that way. It's supposed to say you weigh less. So if your true value is 125, the scale measures you at 130. If I want to know my absolute error, my formula tells me to take the measured amount, so the 130, and I'm going to subtract the true value, 125, and I get 5. And we're talking about pounds here. So what that says is my absolute error is I'm measuring 5 pounds too big because this is a positive. I'm measuring 5 pounds too big. My relative error, if I want to know, well, how big of, how significant is that really? I take that 130, I minus the 125, but then I've got to divide by the 125, my true value, and then times by 100. So I'm going to take that 5 and I'm going to divide it by 125 since I already found the minus part. So I divide by the 125 and then I times by 100. And that's going to tell me my relative error. So that error relative to my size is, listen to me talking like I weigh 130 pounds. That measurement, that's a 4% error. So that 5 pounds represents about 4% when it comes to relative to how the size of the object. All right. So again, in class, maybe we'll do this other example. I don't want the video to run too long, so you'll have plenty of chances to see other ones there. Accuracy and precision. Excuse me. See, I'm trying to speed up and I really shouldn't. Accuracy and precision sound like they're the same thing, but they're actually very different. Accuracy, and I'm going to just read almost straight from these definitions. It describes how close you are to your value. Accuracy is how close you are. Precision describes the amount of detail in your measurement. Okay. Precision is how detailed your measurement was. Accuracy is how close you were to your value. And I love this example over here about Mars, the Mars orbiter, because so in 1999, what happened is there was a problem with the orbiter. So NASA sent very precise instructions to the orbiter. So it uploaded and sent very precise instructions to the orbiter. And what it means by precise is it needed to make some adjustments, and they sent it a measurement in weights. And when I say precise, I mean their measurement, just for example, was 13.1269348. The number of decimals that they accurately measured was ridiculous. It was very, very precise. They were very detailed in the measurement that they sent to the orbiter. The problem is the orbiter was using kilograms, not pounds. So even though their measurement was beyond precise, it was very inaccurate. It wasn't even close to what it was supposed to be because they were measuring with the wrong units. Okay, accuracy is how close you are. Precision is how detailed you are. So suppose your true weight is 102.4 pounds. The scale at the doctor's office can read to the nearest quarter pound. Okay, so you weigh 102.4. We just keep dropping weight like crazy. We're on keto. The doctor's weighs us to be 102.25 pounds. So this is at the doctor's office. The scale at the gym weighs within 0.1 pound. So it says that you weigh 100.7 pounds. So this is at the gym. So it wants to know which is more precise, which is more accurate. Well, the one at the gym only measures out 1 digit past the decimal. The one at the doctor's office measures out 2 digits. So I would say that one is more precise. But which one is more accurate? Well, the doctor's office, if I'm supposed to be at 0.4, I'm 0.15 away. At the gym, if I'm supposed to be at the gym, it says that I'm 100.7. Did I write that correctly? I did. Okay. So the gym says that I'm 0.3 off. So the one that's more accurate is the doctor's office. And I guess you could argue, I would argue almost either way for precision. The one on the left measures 2 digits out past the decimal. It measures to the quarter, but this one measures within a closer range because it rounds to the nearest 0.1. So, I would actually argue that depending on how you could almost argue either way for precision. This one is measuring more decimals, but it can only go by jumps of 0.25. So really, you only have 4 possibilities. The gym, you could have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So I'm changing my answer. I think that the gym, even though there's less digits, I think that would be more precise because you wouldn't have to jump as far to get to the next answer. So I'm gonna change my mind. I think the gym's more precise, but the doctor's office was definitely more accurate. I don't know how they were so far from what the actual weight is, but clearly they're both having some issues there. Okay, combining numbers. There's a couple of things you got to be careful about when you combine numbers together that have been rounded. So there's 2 rules up here. Rounding if you add and subtract, and rounding if you multiply and divide. So for example, a book was written 30 years ago, and it says the Mayan ruins are 2,000 years old. So how old are they now? Well, they were 2,000 years old 30 years ago. So if I take 2,000 and add 30, that means that they're 2,030 years old. Kind of. When we're dealing with significant digits here or precision, it says that we need to round your answer to the same precision as the least precise number in the problem. So when I look at these two numbers, 30 and 2000, which one is the least precise? Well, the 30 gets rounded to the ones digit. The 2000 is getting rounded clear up here to the thousands. So this one is definitely more precise, but we want the one that is least precise, which is the big one. So I'm going to round to the nearest thousands, which means that my 2030 actually rounds right back down to 2000. So even though that was 2000, that was 30 years ago, the Mayan ruins are still 2000 years old. Okay. Now multiplication works a little bit different. The government in a town of 82,000 people is planning to spend $41.5 million this year. Assuming all that money comes from taxes, what's the average amount that everyone's going to have to pay? So if I'm paying 41.5 million, that looks like this. That's the total amount, and it's going to get paid by 82,000 people. So I'm going to divide those. So I'm going to take my 41.5 million. So 4, 5, 1, 2, 3 more. So 41.5 million divided by 82,000 people. That means 506.097. So 506 point, now I can't remember, 0.097. 506.097 per person. So that's how much each person's going to have to pay. But when we round or multiply, it tells us to round to the same number of significant digits as the measurement with the fewest significant digits. Well, 82,000 has 2 significant digits. 41.5 million has 3. So we're going to round to this amount, the 2 significant digits, which means 1, 2 digits right there. So this 6 is going to actually round that up to a 1. So we're going to say that each person is going to pay $510. Now, I didn't actually measure out to the pennies, but we're dealing with money, so I'm going to write pennies in there. Okay. All right. I feel like that's about as much as we should cover today. What we're going to be working on in class is we're going to be doing the homework. What are we on? Homework 3C is the unit that we're on. We're going to do that homework in class. If for some reason you're going to be gone, make sure you do it at home. Keep up with the homework. Don't fall behind even if you're absent. But we'll see you in class. If you have questions, if you need to see more examples, be ready to ask those when you come in.